let E be an algebraic extension of F. By prolongation theorem that we proved, we know that E may be embedded over F into F bar. So this means that there exists a homomorphism sigma from E to F bar such that sigma restricted to F is identity. We give the following definition. The number of embeddings of E into F bar over F is called the separable degree of E over F. And the notation is E over F and with the letter S. We state the following theorem. The first part of it says the following. So suppose we have a chain of extension. Let F sits inside L, which sits inside E. And these be algebraic extensions. Then the separable degree of E over F is equal to the product of separable degree of E over L times the separable degree of L over F. And the second part of the theorem says that if the extension of E of F is finite, then the separable degree of this extension is bounded by the usual degree of the extension, which is the dimension of E over F. Earlier we proved the similar multiplicative property of the usual degree, and now we are going to show that the same holds for the separable degree. And in fact, later we shall see that in many cases the usual degree and the separable degree of extensions are the same. Let's give a proof of this theorem. We can fix one embedding of everything into F bar. And let us count all possible other embeddings of E into F bar over F. Given an embedding sigma of E into F bar over F, let tau be the restriction of sigma to L. So this means that tau is a map of L into F bar. The number of possible taus is equal to the separable degree of L over F. We view sigma as a prolongation of tau. Which means that sigma is an embedding of a larger field into F bar, such that its restriction to L is equal to tau. If tau is equal to identity, then the number of ways it can be prolonged to the map sigma from E to F bar is equal to the separable degree of E over L. And so here we note that since we deal with algebraic extensions, then L bar is the same as F bar. So this is by definition of the separable extension. So we claim that actually for any tau, the number of prolongations sigma of E into F bar with fixed restriction to L is still the same, which is equal to E over L separable. This is true because by prolongation theorem, the map tau of L into F bar extends to the map tau hat of F bar into F bar. So thus we have an automorphism of F bar that restricted to L gives us tau. And then tau hat gives a one-to-one correspondence between extensions of L and extensions of tau of L. This shows that the number of prolongations sigma extending the fixed map tau is the same as the number of prolongations where tau is equal to identity. This tells us that we can count the number of embeddings of E into F bar over F as a two-stage process, where we first count the number of such embeddings for L, and then for each embedding of L, we prolong it to an embedding of E. And what we get is we get this formula. Before we give the proof of the second part of the theorem, let us illustrate this with an example. Take F to be Q, rational numbers, and let E be the splitting field of a polynomial x cubed minus 2. So E is Q with a joint cube root of 2, then cube root of 2 times e to the 2 pi I over 3, and cube root of 2 times e to the 4 pi I over 3. Or this can also be written as just q with cube root of 2 and e to the 2 pi I over 3. And as L, we take just q with a joint cube root of 2. Here we realize these field extensions of Q by embedding everything into Q bar or into complex numbers. There is an alternative approach to constructing these fields, which is independent of such embeddings. We can say that L is isomorphic to Q of x, quotient by the ideal generated by x cubed minus 2. Because x cubed minus 2 is the minimal polynomial of a cube root of 2. Now, how can we construct E in a similar abstract way? To see this, we need to answer the question, So what is the minimal polynomial of cube root of 2 times e to the 2 pi I over 3 over q extended by cube root of 2. The way we compute it is the following. So let alpha be a root of x cubed minus 2. And we don't want to specify what is alpha as a complex number. So alpha may be either of these three roots. What this tells us is that alpha cubed is equal to 2. So then we can factor x cubed minus 2 in the following way. So x cubed minus 2 is equal to x cubed minus alpha cubed. And here we have a factorization formula. We know that this factors as x minus alpha times x squared plus alpha x plus alpha squared. Then we get the answer to this question. So this tells us that the minimal polynomial of this other root is going to be, well, I'll use a variable y squared plus cube root of 2 times y plus cube root of 4. And then this tells us that E may be constructed as q of xy quotient by the ideal generated by x cubed minus 2 and y squared plus xy plus x squared. This is because when we quotient out x cubed minus 2, we get a relation. X cubed is equal to 2. So x plays the role of alpha. And so then this minimal polynomial x squared plus alpha x plus y squared becomes y squared plus xy plus x squared. So this tells us that this ideal is a maximal ideal, because the quotient by this ideal is a field E. Now we count the number of embeddings sigma of E into Q bar. And we view Q bar as a subfield in complex numbers. These are the set of complex numbers that are roots of polynomials with rational coefficients. And we see, so what can happen to L, which is Q of x quotient by x cubed minus 2. So an embedding of L is determined by the image of x. And x here satisfies the relation x cubed is equal to 2. So this means that x may be mapped only to a root of this polynomial. If we call the restriction of sigma to L as tau, then we have three possibilities for tau. So we could have tau 0, where L is mapped to Q with a joint cube root of 2. We could have tau 1, where L is mapped to Q of cube root of 2 times e to the 2 pi I over 3. And we could have tau 2, where L is mapped to Q with cube root of 2 times e to the 4 pi I over 3. In this map, x is mapped respectively either to cube root of 2 or to other two complex roots of this polynomial. If we a priori fixed an embedding of E and L into complex numbers, then the first map can be treated as identity. The number of such embeddings, by definition, is the separable degree of L over Q, which is equal to 3 in this case. And now let us talk about prolongations. So if we take tau 0, so this means that x is mapped to cube root of 2, then there are two ways to prolong tau 0 to a sigma. So here we can map y into cube root of 2 times e to the 2 pi I over 3, because you see both x and y here will be roots of the polynomial x cubed minus 2. We point out that in the field E we have relations x cubed is equal to 2 and also y cubed is equal to 2. So this means that y can also be mapped only to the roots of this polynomial. And the other possibility of sending y is to cube root of 2 times e to the 4 pi I over 3. If we take tau 1, then with tau 1 we send x to cube root of 2 times e to the 2 pi I over 3. Then once we fix tau 1, then we have two possibilities. We can send y to cube root of 2, or we can send y to cube root of 2 times e to the 4 pi I over 3. And there is one-to-one correspondence between these prolongations because we have an automorphism of q bar that sends cube root of 2 to cube root of 2 times e to the 2 pi I over 3. So this is something that we call tau hat. And in this example, we have that the separable degree of E over L is equal to 2. So if we count the total number of embeddings of E into Q bar, then we get that E over Q separable is equal to 3 times 2, which is 6. Now let us prove the second part of this theorem. Here we have E is a finite extension, and we want to prove that the separable degree of E is less or equal to the usual degree. Since E is finite over F and thus algebraic, so this tells us that E can be written as an extension of F with the joint elements alpha 1, alpha 2, alpha n. Then we can consider a chain. So we have F sits inside F of alpha 1, sits inside F of alpha 1 and alpha 2, and so on, sits inside E. We point out that it is sufficient to prove this inequality for each step. And then we know that the overall separable degree is the product of separable degrees at each step, and the overall degree of this extension is also a product of degrees at each step. If we have this inequality for each step in this chain, then we get this inequality for the extension of E of F. So it's sufficient to take E to be F with a joint a single element. Now let F be the minimal polynomial of alpha over F. Then the degree of F of alpha over F is equal to degree of this polynomial, since F of alpha is isomorphic to F of x, quotient by the ideal generated by little f. But what is the separable degree of F of alpha over F? So this is the number of distinct roots of F in F bar. Because when we consider embeddings of F of alpha into F bar, alpha has to go to one of the roots of this polynomial. And we know that the number of roots of a polynomial cannot exceed the degree of this polynomial. And this gives us the desired inequality. We give the following definition. A finite extension E of a field F is called separable if the separable degree is equal to the usual degree. So the separable degree is the number of embedding of E into F bar that fixes F, and the usual degree is the dimension of E as a vector space over F. Let E be F of alpha, where alpha is algebraic over F. And let little f be the minimal polynomial of alpha. Then we see that extension f of alpha is separable if and only if this polynomial f has no multiple roots. This holds because the usual degree of this extension is the degree of the polynomial, and the separable degree is equal to the number of roots of f in the algebraic closure of the field. Now let us prove the proposition. If characteristic of the field is equal to 0, then any irreducible polynomial f in f of x has no multiple roots. Proof. So we observe that f of x is divisible by x minus alpha squared if and only if both f and f prime of x are divisible by x minus alpha. So what we see is that f of x has multiple roots if and only if the greatest common divisor of f of x and f prime of x is not equal to 1. In this claim, we do not assume that polynomial f is irreducible. But now, let's assume that it is. So suppose f is irreducible and has degree n. If characteristic of the field is equal to 0, this implies that the degree of the derivative is precisely n minus 1. And an irreducible polynomial of degree n cannot possibly have common factors with a polynomial of degree n minus 1. So from here, it follows that the GCD of f and f prime is equal to 1. And this means that f has no multiple roots. This gives us a corollary. If the characteristic of a field is equal to 0, then every finite extension of the field f is separable. What can possibly go wrong here in characteristic P? Well, it turns out that in characteristic P, it's possible that a non-constant polynomial has a zero derivative. And then non-constant irreducible polynomials with a zero derivative will give rise to non-separable extensions. This situation is called purely inseparable extension. Let's give an example. As a field, let's take the field of rational functions over Zp. Elements of these fields are quotients of two polynomials with coefficients in a finite field Zp. Consider the following polynomial. F of x is equal to x to the power of p minus t. We point out that t is prime in the ring Zp of t, in the polynomial ring. And then by Eisenstein's criterion, the polynomial x to the power of p minus t is irreducible. But what is the derivative of this polynomial? When we differentiate x to the power of p minus t, we're going to get p times x to the p minus 1. But since we are in characteristic p, this is 0. So what we get is we get a non-zero polynomial of degree p with a zero derivative. Let alpha be a root of x to the power of p minus t in the algebraic closure of f. Then it satisfies the following relation. Alpha to the power of p is equal to t. Let us consider x minus alpha to the power of p. Using binomial formula, this is equal to the sum k goes from 0 to p choose k, times x to the power k times minus alpha to the power of p minus k. But this binomial coefficient will be divisible by p unless k is equal to 0 or k is equal to p. So this means that most of these terms will vanish in characteristic p, and what we get is x to the power of p minus alpha to the power of p. And because alpha to the power of p is equal to t, so this is our polynomial, x to the power of p minus t. This tells us that this polynomial, x to the power of p minus t, factors in this way. So the conclusion is that this polynomial has a single root with multiplicity p. And we should think of this alpha as pth root of t. So now, if our field, we take f extended with alpha, then what we get is we get that the degree of this extension is equal to p, since p is the degree of this irreducible polynomial. But the separable degree of this extension is equal to 1, because the separable degree is equal to the number of distinct roots of the irreducible polynomial that defines this extension. And such extensions are called purely inseparable extensions. Let us discuss how separability behaves under taking chains of extensions. We have the following proposition. Let f be contained in k, and k is contained in E, be finite extensions. Then E is separable over F if and only if E is separable over K and K is separable over F. Let's give a proof. by definition, E is separable over F if and only if the separable degree is equal to the usual degree of the extension E over F. But we know that both usual and the separable degree are multiplicative. So that is the degree of E over F factors as degree of E over K times degree of K over F. And the same is true for separable degrees. We also know that the separable degree cannot exceed the usual degree. Because of this bound, we have equality in the left-hand side if and only if the corresponding factors in the right-hand side are equal. And this completes the proof of this proposition.